Okay, welcome to the second session of the morning. It was not entirely clear what time we should start, but I think we're filling up and it's good to keep on going. Let me also first thank the organizers for putting up this fantastic meeting here. So this will be another interesting session, and we'll start with a talk by Daniel Grumiller.
Okay, so let me also start by thanking the organizers, especially Ahmed, for this opportunity and the invitation. And it's my first time in Abu Dhabi, and it's been very enjoyable so far. And speaking of first times, I think this is the first talk with Carroll in the title at the Strings Conference, so therefore I decided to organize my talk largely as a review. And I'll start with basic questions, namely what, why, and which. So what are Carroll symmetries? They are space-time symmetries, and they complement the well-known Aristotelian, Galilean, and Lorentzian spacetime symmetries. And the distinguishing feature is that space is absolute and time is relative. So you can picture the current spacetime as emerging from a C to zero limit of a Lorentzian spacetime, and as a consequence of this, the light cone collapses. So this led to the limiting definition of Carroll spacetime as a C to zero limit of Lorentzian spacetimes, and that's the way that they were originally discovered 60 years ago by Levi-Leblanc, who also gave the name Carroll, inspired by Lewis Carroll, the author of Through the Looking Glass. Now, since it's hard to envisage physical applications of a C to zero limit, you can understand why it took about half a century before people started getting more interested in these Carrollian symmetries. There's an intrinsic definition as well that requires an extension of our notion of signatures that will allow for the metric. So Carrollian spacetime you can understand as a metric with signature 0 plus plus plus, so that means there's no proper inverse, plus a vector field in the kernel of that metric. And the simplest example is a flat Carroll spacetime, the C to zero limit of Minkowski, and the Carroll metric is essentially the spatial part of the Minkowski metric, delta ij, and the vector field is just dt. And Carroll boosts, in this case, shift time by linear expression in X with some boost parameters bi and leave invariant space. Now, why would anyone be interested in Carroll symmetries? I give one reason on this slide. And to answer this, let's look at the Carroll conformal symmetries by solving the Carroll conformal killing equations. And the solution is given by this Carroll conformal killing vectors. The first part contains an arbitrary function of space. So this part generates x-dependent time translations, also known as super translations. The best known examples are, of course, just standard translations. Then when t is linear, you get Carroll boosts. And when t is quadratic, you get temporal special conformal transformations. So here you see already the first big difference to Lorentzian spacetimes. Even in finite dimensions, bigger than 2 and smaller than infinity, you have infinitely many Carroll conformal killing vectors. The remaining part is identical to the Lorentzian case, so you get spatial translations, rotations, dilatations, and special conformal transformations contained in these functions yi. So overall, this is the Carroll conformal algebra in the spacetime dimensions. The part in black is identical to the Lorentzian counterpart, and the part in red is new, and these are exactly the super translations, and there are infinitely many of them. Now, a bit more than 10 years ago, in its most general form, it was shown by Duval, Gibbons, and Trovati that the Carroll conformal algebra is isomorphic to the BMS algebra in one higher dimension. So that means, well, BMS, as you know from previous strings conferences, are the asymptotic symmetries in asymptotically flat spacetimes. And the easiest way to see the Carroll metric is to look at scry. So for instance, at scry plus, the metric is while related or conformally related to this metric here. The first part is just a metric on the celestial d-2 sphere. And then you have a term minus 1 over r squared, which goes to 0 as r goes to infinity, times the u squared. U is the retarded time on the light cone. And therefore, u is just the Carroll time in this specific example. So therefore, it's suggestive that Carroll symmetries are of relevance for flat space holography. And instead of something like an ADS-CFT correspondence, we could have a flat CCFT correspondence where CCFT stands for Carrollian CFT. Okay, besides this flat space holography motivation, there are additional motivations which I'll not discuss in detail. I just listed them here. The first one is half a century old, and most of them emerged just in the past couple of years. On this slide, I want to show you some details of the Carroll conformal algebra, but I don't want to memorize all these commutators. I'll just focus on one important one. The part in black is again identical to the Lorentzian counterpart. The part in red can be summarized by saying that supertranslation commuting with anything gives another supertranslation. Unless you commute two of them, then you get 0. And there are various generalizations. The first one is rather natural. You can allow for anisotropic scale invariance. You can't do this in the Lorentzian case without breaking Lorentz boosts, but you can do this in the Carrollian case without breaking Carroll boosts, because in the Carrollian case, you already discriminate between space and time. So anisotropy is very natural there. You can lift some restrictions on the yi, generalized to, for instance, superrotations or spatial diffeomorphisms. You can further generalize to the Carroll diff algebra, where T depends on time and space. There's also a way to gauge the finite Carroll algebra to get Carroll gravity in the same way that you get Einstein gravity from gauging Poincare symmetries. And finally, you can do supersymmetric or higher spin extensions. Now, the finite Carroll algebra is a subalgebra of this. And the most important commutator, the one that I want you to memorize, is the one displayed in red. So the Hamiltonian commutes with Carroll boosts. And that's different not just from the Lorentzian counterpart, but also from the Galilean. And it's physically quite surprising. It means when you have a physical state and you boost it, you don't change its energy. And that's behind many of the physically unique features of Carrollian systems. And it manifests itself in, well, various systems. For instance, flat bands, you can think of them as the Fourier transformed version of the light cone closing up. So in Fourier space, the light cone opens up, and you have a dispersion relation where energy is independent from the momentum. The second computational relation is like in the Galilean case. It just means that Carroll boosts commute with each other, so you have no analog of Thomas precession. And together with the third commutator, you see that translations and boosts generate the Heisenberg subalgebra of the Carroll algebra, where the Hamiltonian is central. And these generators, they are not just Carroll conformal killing vectors, but actual Carroll killing vectors, so they preserve the Carroll structure. Now, you might suspect that something special happens in 1+1 dimensions, and this suspicion is correct. So in CFT2, we have two copies of the Virasoro algebra with some central extension C plus minus. In holographic CFTs, these are given by the Brown-Inot values, 3L/2G, where L is the ADS radius. And you can generate the Carroll conformal algebra through an Wigner contraction in this way. So you define superrotations as the difference of the Virasoro generators and supertranslations as the sum, rescaled by 1/L, and then you take the L to infinity limit, and you contract to the Carroll conformal algebra in 2 dimensions, displayed here in this box. The first line shows that you have always a Virasoro subalgebra generated by the superrotations, but the central charge here is typically 0. It's always 0 if your parent CFT didn't have a gradation anomaly, because the central charge is always given by the difference of the central charges C plus and C minus. The central charge appearing in this mixed commutator, which I refer to as BMS central charge, is given by the sum, but rescaled by 1/L. So if you start with any minimal model CFT, or any CFT where the central charges are finite, you always end up with a trivial result, namely Cm is equal to 0. However, for holographic CFTs, the central charge scales linearly in L, so therefore these L's cancel, and you get a finite result given by 3/G. So this is the result of relevance for flat space holography. Okay, now I come to the main statement. So it's based on this fact that I mentioned already, that the Carroll conformal algebra in d dimensions is isomorphic to BMS in 1 higher dimensions, and therefore it's natural to conjecture that a Carrollian CFT in d dimensions is the field theory dual to asymptotically flat gravity in d+1 dimensions. There's an interesting history which I will not get into. Let me just mention that, interestingly, many of the flat space holography results were pioneered in the 60s, BMS in 62, the Carrollian symmetries in 65, and the soft gradient and photon theorems also in 65. And then it took half a century to realize that all these things are connected. Okay, so to test this conjecture, we should calculate physical observables like correlation functions, establish a Gobser-Klebanov-Polyakov-Witten type of dictionary, thermal entropy, entanglement entropy on both sides of this conjectured correspondence. And I'll focus in the remainder of my talk mostly on 3 bulk dimensions. So I'll show you one such example, namely stress tensor correlation functions. I'll start with the field theory side. So in a Carroll and CFT2, you have an analog of the stress tensor. I work here on the cylinder, so coordinate phi is going to be 2 pi periodic. And the super translation operator is given by the Fourier modes mn, and then shifted by the vacuum value minus Cm over 24. The super rotation operator is given by, similar the Fourier modes of Ln. And then you have this additional shift minus I and U mn, which I'll explain in a second. And if Cl was non-zero, then you also have this vacuum shift. Now, these results are compatible with the Carroll conservation equations or the Carroll conformal ward identities. So these are analogs of the corresponding CFT conservation equations of the stress tensor. And they tell you that dum is equal to 0, but dun has to be d phi m, and that explains this additional term that you have to have here. Now, as a consequence of this Carroll conformal ward identities, you get these results for the 2-point functions on the cylinder. So 2 super translations give a vanishing correlation functions. By m1, I just mean m evaluated at Carroll time u1 and angular coordinate phi 1. Then the 2-point function involving 1 super translation, 1 super rotation gives a result that looks like a CFT result. So Cm over 2 S12 to the 4, where Sij is 2 sine phi I minus phi j over 2. And finally, the 2-point function involving 2 super rotations gives a Carroll CFT result, Cl over 2 S124. And then shifted by minus 2 Cm tau 12, where tau ij is the difference of Carroll times dressed by some angular function. And like in the CFT2, these results are entirely dictated by the symmetries and by the values of the central charges, so there's no freedom. Similarly, the 3-point functions are uniquely determined in the same way. I'll not discuss them here. And again, similarly to CFT2, when you go to 4 and higher endpoint functions, you get 3 functions of conformal cross ratios that are not determined by symmetries. But if you look at specific operators, of course, they are still determined. So for instance, if you look at this specific 4-point function involving 1 super translation insertion, 3 super rotations, you get a function of the conformal cross ratios, G4, that is a simple rational function that you can compute. And to get all the higher endpoint functions, you can establish Belavin-Polyakov-Samolochikov type of recursion relations that allow you to determine the n plus 1 point functions from lower point functions. So you can start with the 2-point functions and then work your way up to any n-point functions. So the n-point function involving 1 super translation insertion is given by corresponding n minus 1 point functions on which you act with this operator, and then you sum over all possibilities up to these connected terms. And assuming Cm is non-zero, you can determine the n-point functions involving just super rotations from correlation functions of this type. And correlation functions with 2 or more super translation insertions, they all vanish. So in this way, you get all the correlation functions from 2-point functions together with these recursion relations. So can we derive this also on the gravity side? The answer is yes. I'll briefly show you how. It's convenient to use the Chern-Simons formulation of 3D gravity with an ISO 2,1 connection. And people familiar with ADS3 CFT2 results will recognize some of these formulas. So we go into a holographic gauge, which means we split the connection into some fixed group element that is state independent, depends only on the radial coordinate, and the boundary connection A that contains 2 state-dependent functions m and n. And you can prove that the flat space Einstein equations imply the ward identities, the Carroll conformal ward identities. So on shell dum has to vanish and dun has to be d phi m. And then to derive correlation functions, we have to add chemical potentials as sources or non-normalizable modes. We do this in the usual way, so we shift the 0 component of the connection by chemical potential for super translations and super rotations, and the rest is completely determined on shell. And then we proceed more or less in the standard way, so we localize sources at insertion points of endpoint functions, and this is analogous to the CFT2 construction of 2-point correlators from 1-point functions where you deform the CFT with a source mu of z, couple it to the stress tensor, and localize it at the insertion point, dressed by some bookkeeping parameter epsilon in which you linearize. And then the 1-point function of the deformed CFT is given by the 1-point function of the original CFT, plus an order epsilon term that computes the 2-point function. So in this way, by calculating this 1-point function, you get the desired 2-point function. And when you do this in this flat space Einstein gravity context, for a single localized source, you indeed recover the CCFT2 2-point functions, but I'll not guide you through these details. You can read the slide afterwards or look up the calculation in the paper if you're interested. And then by complete induction, you can localize n times instead of n-1 times, and that yields precisely the BPZ type recursion relations that I've shown to you on the previous slide. So as a conclusion of this, all the CCFT2 stress tensor endpoint functions are reproduced on the gravity side. So if you take the 42nd derivative of the Einstein-Hilbert action, or 42nd variation, you indeed reproduce the Carrollian CFT 42-point functions. So that's a consistency check that 3D flat space holography can work, and it's entirely based on symmetries, so there's no check beyond symmetries here. Earlier checks that are entirely based on symmetries are a derivation of a Cardi-like formula and calculation of entanglement entropy and its holographic counterpart, but I'll not discuss them in my talk here. So for the last part, I want to move to the field theory side. So the premise of this slide is that it's worthwhile to explore Carrollian quantum field theories and Carrollian CFTs. And I decided to start with an equation that was labeled by Schwinger as the most fundamental equation of relativistic quantum field theory. So it's the commutator of energy densities evaluated at different points. It's given by this expression where hi are the momentum densities. And as Schwinger and before him Dirac observed, this commutator must be of that form due to Poincare invariance. So since we no longer have Poincare invariance in Carrollian field theories, it's fair to ask how is this commutator changed? And the answer is actually very simple. The result vanishes. So in Carrollian quantum field theories, the energy densities have to commute. And that's an important consistency check. So if you are inspired to do some model building using Carroll quantum field theories, that's an important consistency check that you can perform. Now, if you want to obtain Carroll quantum field theories as a limit of ordinary Lorentzian quantum field theories, then there's an interesting subtlety. Namely, there are two such limits, electric and magnetic. Obviously, these names derive from applications in Maxwell's theory, but here I'll focus on the free scalar field example for illustration. So let's take just the free massless Klein-Gordon field in Hamiltonian formulation with momentum pi and field phi. And then when you set c, the speed of light, to 0, you immediately get the so-called magnetic limit. And then pi no longer is a momentum, but rather a Lagrange multiplier for a constraint dt phi equal to 0. And the remaining equations of motion are just Laplace phi equal to 0. So this is a very boring system. There's no propagation at finite speed, but you should expect this because the light cone collapses, so there's no actual propagation in this theory. The other limit, the electric limit, is obtained if you first rescale the momentum by c and inversely rescale the field. That preserves the symplectic form, and then when you take the c to 0 limit, this last term vanishes, so you end up with a limiting action where you can still integrate out the momentum, and then the action is just 1/2 dt phi tilde squared, and again the equations of motion are very trivial, just the second time derivative of the scalar field vanishes. So in neither of these cases you get propagation at finite speed, which again is something you might expect. So it's an interesting question to ask, can you go around this? So is there some Carroll invariant interacting fields with finite propagation speed? And the answer is yes. We call this Swiftons. It's just the English version of tachyon, but I'll explain why we didn't call it tachyon. So the technically key issue is that the inverse on the quotation mark metric, G mu nu, is not Carroll boost invariant. And as a consequence of this, you cannot just raise indices, in particular not spatial indices, unless you impose some additional constraints. So we saw this implicitly already in this magnetic Carroll scalar field. There, the theory was only consistent if we impose this constraint dt phi equal to 0. So this generalizes. If you consider a covector theta that is transverse to the Carroll vector, then you can easily prove that the norm of this vector is Carroll boost invariant. And you can exploit this to construct interaction terms. So the simplest example is if you have two scalar fields, phi and chi, you take the first derivatives, you antisymmetrize, and you contract once with this Carroll vector field, then this theta mu is indeed transverse, and you can use it square as an interaction term. So this leads to the simplest Swifton action. It consists of two electric kinetic terms and this interaction term. So you have v mu d mu phi squared plus v mu d mu chi squared plus g theta squared. And this was first discovered in a non-Carrollian context, in the context of space-time subsystem symmetries by Baik, Dislakar, Russ, and Sun a bit less than 2 years ago. Now, you can show that indeed the energy density here is compatible with the Carroll condition, that H commutes at different points. This is as it must be, but it's somewhat non-trivial to see this because H of x for this model is a quite complicated expression. Moreover, you can show that the energy density is bounded from below, and that's why we refrain from calling these tachyons and use instead this alternative name, Swifton. And finally, if you consider a specific exact background of this model, namely phi is equal to t and phi is 0, then you can show that fluctuations in phi propagate actually with a finite speed that is determined by the coupling constant of this Swifton interaction term. So c squared effective is minus g. Yes, thanks. Okay, so I'm already on my last slide, so let me, well, okay, not quite. I have one more point to make. So there's something interesting going on when you send C to 0. We refer to this as tandem gravity limit. So there are various no-go results or apparent no-go results for Carroll field theories. No propagation, but we just saw you can go around this using the Swiftons. There's no obvious Carroll thermodynamics. So this is from this Carroll stories paper by De Boer, Hartung, Oberst, Sibesma, and Van Doorn. And there's also no obvious interacting Carroll quantum field theory. So in this paper by Kotler, Jensen, Prohaska, Ras, Riegler, and Salzer. Now, let's address the second point here. I don't have any good answer to the third one yet. So let's consider implications of the C to 0 limit for black hole observables, keeping fixed the energy. This is a very basic exercise here. You can see that temperature, entropy, and horizon radius all either diverge or go to 0 if you send C to 0. But you can get finite results if you do a triple scaling limit. So if you keep fixed C to the 4 over G Newton, sometimes referred to as the magnetic gravitational coupling constant, and also H bar times C when you send C to 0, then all these quantities are finite, and this is what we refer to as tandem gravity limit. So in this compactified Bronsted cube, it means you go to this corner, TG, where C is 0, H bar is infinite, and G Newton is also 0. All right, so let me give you some outlook. I haven't talked about scattering amplitudes in my talk. Obviously, they're very important observables in asymptotically flat space. And there has been some progress in the past couple of years relating celestial and Carolin holography. So there's a dictionary that translates celestial amplitudes into Carolin amplitudes, starting with this work by Donei, Fiorucci, Erfrey, and Ruzzicone, and at the same time Bakshi, Banerjee, Basu, and Dutta. So this applies to 4 dimensions. Most of these papers apply. But very recently, there's a long-awaited paper by Kotler, Jensen, Prohaska, Riegler, and Salzer, which made substantial progress in 3 dimensions. There you have to add, of course, massless fields if you want to have some scattering to scry. Brief summary of this relation is that when you take a celestial amplitude, you do an inverse Mellin transformation and you Fourier transform, then you have Carolin correlators. So these correlation functions obey the Carroll conformal word identities, and radiation is encoded in external sources in a CCFT. I can't say anything about black holes, so this is something for the future. That's obviously important because it inspired the very notion of holography, but so far we can't say anything. In 2+1 dimensions, we don't have black holes, so that's why we can't say anything. We only have flat space cosmologies, which are still solutions with horizon, but not black holes. And in 4 dimensions, this issue hasn't been addressed very much yet. There's also some string constructions where Carolin symmetries pop up, notably in the tangent-less limit. And I won't get into details here, but let me just point out there are at least 2 different notions of Carroll strings. You can take a Carolin limit either on the world sheet or in target space. And finally, I think it is a good time to start trying to classify Carroll CFTs, taming the zoo of the diverse Carroll conformal symmetries, construct examples of various Zoom members, and find candidates for holographic CCFTs. As I indicated, it's much harder to come up with good examples for Carolin CFTs because we don't have an analog of minimal models, and we can't, when you take the limit of minimal model CFTs, we get something trivial. Finally, just as a reminder, there's a bunch of other applications outside of flat space holography, and this word cloud here is based on actual bibliographic data. Okay, so as a last statement, I think it's true that once you've seen Carroll symmetries, you cannot unsee them, and there that may explain the recent increase in Carroll papers on the archive and on Inspire. So I'll stop here and thank you for your attention.
Thanks a lot. Questions from the audience? In the back, Raju?
So I had a question which wasn't manifest in the symmetry analysis that you did, which is where do these Carolian CFTs really live? And the reason I asked that is from the bulk, if you do an analysis, the constraints tell you that every observable on null infinity can be represented at its past boundary, and on future null infinity can be represented in its past boundary, and similarly for past null infinity on its future boundary. So somehow this Carolian CFT should live at the boundary of null infinity, or maybe on spatial infinity. Is there some indication of that? I mean, this should be somehow important because it's important in the bulk. Yeah.
So, okay, the dual CFT is supposed to live at scry, not just at the past or future boundary of scry. So the Carolian time is precisely played by retarded or advanced time. So retarded time U plays the role of Carolian time.
I see, but if you have all of scry, then you can represent data for even a non-gravitational theory in the bulk, right? So somehow holography should give you a reduction. It should take all of scry and put you down to, codimension 1 of scry.
Well, it's true that whenever you have a null hypersurface, you do get Carolian structures on the null hypersurface. That much is true. But to establish something like Carolian holography, you want to start with some gravitational theory in the bulk. And I mean, the checks that I presented, they rely on the BMS charge to be non-zero and given by 3/G Newton. So there you need as input Newton's constant.
Okay, thanks.
There's a question here.
Just a curiosity, are there also interesting Carolian structures near black hole horizons that are interesting, that are different from the Carolian structures that scry in any interesting ways?
Yes.
And do they smoothly interpolate into near horizon geometries as well? There's been some recent work on near horizon.
So in 2+1 dimensions, you can do this. You can do a smooth interpolation between symmetries near the horizon and the Brown-Inot symmetries at infinity. But in 4 dimensions, I don't know exactly how to interpolate between the near horizon symmetries and the asymptotic symmetries. But you can
horizon ADS region sort of smoothly as
Sorry?
Maybe in some extremal black holes, maybe some near horizon.
Well, for
ADS
extremal black
regions.
holes, I don't know. So the statement that I made applies actually to non-extremal black holes. There you get you can recover BMS. For extremal black holes, it seems actually a bit harder to recover BMS symmetries, but that doesn't mean it's impossible. It's just we haven't done this yet.
Other questions? Over there.
Yes. Can we start with an example of ADS-CFT and take the Carolian limit to get a well-defined example of flat space holography? Is this limit well-defined, or is it singular and one has to do more?
I mean, we tried to play around with n=4 super-Young mills and then got confused with how to scale n versus how to taking the Carolian limit, and there seem to be several inequivalent ways of taking the limit. And on the field theory side, in 1+1 dimensions, one of the issues that I mentioned is that when you keep the central charges finite while taking the limit, you end up with a trivial Carolian CFT. That's not what you want. But there's an example, which is more complicated, but if you take Liouville theory, there's a Carolian limit of that. So you have a Carolian version of Liouville CFT, and that was derived from the gravity side as a boundary action in the spirit of Alexeyev-Shatashvili by Gomborov, Gonzalez, and Barnich more than a decade ago.
I see. What if one takes these limits directly at the level of these gauge invariant observables? Do you still see multiple structures?
The experience is that it's often hard to obtain the correct results as a limit unless you know already what the correct results are. The subtleties are that, as long as C is finite, or whatever your contraction parameter is, you can do field redefinitions that involve C, you can do C-dependent gauge transformations, and they don't matter, but they do matter when you take the limit. And A simple example of what goes wrong in context of ADS-CFT is if you just take the Pfefferman-Gram expansion and send the ADS radius to infinity, you get garbage. That's not the right limit. So you have to do first an L-dependent gauge transformation into Bondi gauge, then you can take the limit L to infinity, and then you get the right flat space limit. So if you know the result, it's usually easy to recover it as a limit, but if you don't know the result yet, you have to guess, and when you guess, chances are you guess wrong.
Thanks.
Other questions? I allow myself a quick question. So you showed in your sort of double-scale tandem gravity limit that black hole thermodynamics survives.
Right.
So are there putative semi-classical solutions associated with that? And what do you envision are the types of equations of motion they actually solve?
Yes, those solutions would be Carroll black holes. So these are solutions not with a horizon, but with a Carroll extremal surface. And they solve solutions of Carroll gravity. Yeah.
And yeah,
That's one example.
would it be electric or magnetic? Yeah, that's.
This is magnetic. Yeah. Magnetic. They're always magnetic. Yes.
Okay, let's thank Daniel again. Great. And the next speaker is Anna Maria Raclariu, and she will give a talk on boundary actions. Thank you.
Yeah, so thank you very much. I would like to start by thanking the organizers for putting together this wonderful conference and for inviting me to speak. So I'm going to be talking about some recent work with Tempo He and Catherine Zurek from Caltech. So the motivation for this work is trying to understand to what extent holography generalizes beyond ADS-CFT. And one concrete example that one can study is theories of gravity in asymptotically flat spacetimes. So here, the main observables, or really building blocks of observables, are expected to be scattering amplitudes, which are related, as we sort of heard from Daniel's talk already, either via a Fourier transform or a Mellin transform to a Carrollian, to sort of Carrollian observables, or to the celestial observables. So the Carrollian point of view is that the boundary theory would live on some on this null boundary of an asymptotically flat spacetimes, whereas in this celestial conformal field theory perspective, the boundary theory would be living on a sphere, so on a codimension 2 slice in space-time, which is really obtained from, whose observables are obtained from the Carrollian ones by performing a dimensional reduction, basically by integrating out these null directions. Now, a lot of things are understood at this point that have to do with kinematics mostly. So it's well known that gravity in 4-dimensional asymptotically flat spacetimes has a very rich symmetry structure near the boundary, so both in terms of asymptotic symmetries and in terms of phase space symmetries. So an example that's already visible at the level of scattering amplitudes are soft graviton modes. So these are given in terms of these moments of the News tensor. We've seen similar expressions in Sasha's talk, but here these are defined, they should be defined in the theory of gravity. And these were relatively recently shown to be related for every integer n here to higher spin currents in this 2-dimensional conformal field theory that form a higher spin symmetry algebra, namely a W infinity algebra. So I'm not going to talk about this in this talk, but instead I'd like to ask a question about, namely, what other entries in the holographic dictionary you would expect to find. So I'm going to put forward two sort of questions that one can ask, both of which draw inspiration from ADS-CFT. So the first one is a lesson from old days of ADS-CFT, which is that the ADS partition function with specified boundary conditions acts as the correlation function of primary operators in a conformal field theory. So the way this works is that in ADS, near the boundary, there is, in simplest examples, there is usually two kinds of modes. One of them is growing, the other one is decaying. The growing one is a non-normalizable mode, and one usually imposes that these non-normalizable modes are fixed. And hence, this partition function with fixed, these modes being fixed, then acts as the generating function for correlation functions of operators in the boundary CFT. In the semi-classical limit, here the relevant object that would enter in this computation of the partition function with the sources turned on would be the on-shell action. The question that I would like to ask is whether a similar relation exists in gravity in asymptotically flat spacetimes. Now, on a different sort of line of thought, but still inspired from many studies, many findings in the context of ADS-CFT over the past many years, is this proposal, perhaps a bit more controversial, of Ferninde and Zurek, which claims that vacuum space-time fluctuations in quantum gravity could be observable. So I'd like to briefly describe the idea here. So it relies on defining this object, which in Minkowski space would just be the boost generator, but for a special geometry, which is the space-time that has a shock wave in it. And the shock wave is basically generated by an ultra-relativistic particle with stress tensor TUU that's localized at a particular retarded time. So here we've already seen a picture like this in Sasha's talk. U and V are light cone coordinates. And so this particle sources a geometry that is just flat space plus the shock wave HUU. The interesting thing is that if one probes this geometry with another particle that propagates here, we expect from causality that, and actually just from analyzing the geodesic equations in the space-time, that the particle will acquire a time delay. And this time delay is directly related to HUU and hence this stress tensor. So plugging in these two equations into this formula, we find that this kappa operator is an operator bilinear in these two fields. And I'd like to emphasize that typically in semi-classical, when one tries to go away from the classical limit, one promotes this T to an operator but keeps this boost vector field, the function that enters in the boost vector field, as a function. But what Ferninde and Zurek proposed was to actually promote this parameter of the boost also to an operator, and hence we find an operator that's bilinear in these two guys, both regarded as operators. And then this was sort of inspired by older ideas by Tooft, who assumed or really postulated that in a theory of quantum gravity, these two variables appearing here should be canonically paired to one another. And this comes from the intuition that this setup can be thought of as the scattering of two shock waves, and in the quantum theory, the shock wave should acquire some width. And so these two guys cannot be determined with certainty. Okay, so now taking this commutator seriously, one can compute fluctuations in this operator, which, sorry, I should have said that these operators from ADS-CFT, we know that they are expected to capture some properties of areas of causal diamonds in space-time. And so one can compute fluctuations in this operator. They are badly divergent, but they basically, so they scale as the area of the causal diamond times some singular delta function, which when regulated by, assuming that this can be regulated by 1 over the Planck length squared, one then finds this funny relation between area fluctuations and areas of causal diamonds, which leads to basically enhanced fluctuations of these areas. So this calculation is inspired by ADS-CFT, as I said. It's, of course, it's very much in contrast with the expectation from linearized gravity, where the 2-point function of gravitons scales as the Planck length squared. And so the question I'd like to ask is whether we can find, or maybe more rigorously define an operator analogous to kappa that captures area fluctuations in asymptotically flat spacetimes. And there's two reasons why one might expect that to be the case. So one of them is that in asymptotically flat spacetimes, we have asymptotic charges, and these are rigorously defined, and they are also diffeomorphism invariant, typically. And so perhaps one could think that these operators are related to some sort of charges, some sort of asymptotic charges. And the second reason is sort of motivated by some previous works, is that these shockwave geometries actually turn out to be related to spacetimes that are Minkowski, plus instead of a shockwave, so metric deformation that is it is HUU at order 1, instead by gravitational memory. So this I'm going to describe later on. So these two are related by gauge transformation, and so if one is able to construct a diffeomorphism invariant observable in either case, that should capture the physics in either theory, the same physics in either theory. So this brings me to the main results and the outline. So the main results are basically very partial answers to these two questions that I raised. And the answers are as follows. So as for the first question, I'm going to show that one can construct an on-shell action in the infrared sector of four-dimensional asymptotically flat spacetimes. So I'm going to define this in just a moment. And we'll see that this on-shell action actually acts, or rather the partition function associated to this action acts as the generating function for correlation functions in a two-dimensional conformal field theory that captures soft graviton, or really amplitudes involving soft gravitons in 4 dimensions. And the second point I'd like to make, and this is a bit more, it's not very well established, but I will describe it nevertheless, is a relationship between this operator kappa and soft charges, or really generalization of soft charges, or soft supertranslation charges in particular in asymptotically flat spacetimes. So the plan is as follows. I'll first describe soft modes in 4-dimensional asymptotically flat spacetimes to set the stage for the problem. And then I'm going to show how to construct these boundary actions and how they are related to the CFT2 correlators. And then I'm going to focus on these soft charge fluctuations. So the setting, so I'm mostly going to be working in the bulk. So the talk is not going to have to do much with celestial or Carrollian field theory. So we'll consider solutions to Einstein's equations that at large radius r reduce to Minkowski space. So here I'm working in coordinates in a retarded. I'm going to mostly focus on retarded coordinates, so on the experience of an observer that is really far away in the future. So u is the time minus the radius, and then we have spherical coordinates. So radius and z and z bar that are just coordinates on spheres that are basically cuts on these cones at the boundary. So the solutions take the following form using standard boundary conditions. So we impose that as r goes to infinity, the metric reduces to Minkowski space, and then we have subleading corrections in powers of 1 over r. So the solutions, it's well known that they are parametrized by a function of u, by functions of u, z, and z bar that are called, tensors really, that are called the shear, as well as the derivative of these tensors that are called the news. And in particular, if this news tensor is non-vanishing, this means that we have gravitational radiation or gravitational waves. Then the equations of motion, so really Einstein's equations, then determine the evolution of the subleading components in terms of these free data. So just as an example, we have the time derivative of the body mass aspect is given in terms of the news tensor in the following way. And just to check that this makes sense, if we integrate both sides on the sphere, we find that the time evolution of the net body mass is, so this term goes away, and we find that the Bondi mass decreases as a function of retarded time because this object is positive definite, and this makes sense because it just tells you that energy is lost through gravitational radiation. So now I'm going to do, so these solutions were quite general. Now I'm going to restrict to a particular, the simplest kind of solutions that one can write down, which are given by shears that take the following form. So they have two components. One of them is this function CZZ. And you can think about this first term as the zero mode of the shear. And this has been shown in previous works that it labels the vacuum degeneracy that one can have in asymptotically flat spacetimes. And then I'm going to introduce a minimal kind of time dependence, which is represented by this function n multiplied by this step function in u. And this is really related to the presence of soft gravitons at infinity. So in particular, if one takes the integral over time of the news tensor, one basically obtains dz squared of n. And if you think about what this is, it's just really the zero frequency limit of the Fourier transform of the news. And upon quantization, that's really just a graviton. Okay? Another way to think about this is that the time integral of the news, given that the news is the time derivative of the shear, we also find that we obtain this integral to be given by the difference between the shear at the past boundary of Scri plus and the shear at the future boundary of Scri plus. And this is nothing but the gravitational memory effect. And it's been shown and well known by now that soft gravitons are related to the gravitational memory effect in asymptotically flat spacetimes. So it's a fact now, again, well known that these two functions, C and N, become, well, variables on the gravitational phase space and are canonically paired. So to see that, we can consider a Lagrangian form associated to our standard scalar Lagrangian and consider its variation. So the variation of the Lagrangian, as usual, is given by the equations of motion times the variation of the fields plus a boundary term. And so this theta that appears here is known as the presymplectic potential. And upon integrating this term in space-time, this localizes on the boundary. And there's two things that one can do. So first, one can consider evaluating this theta on a Cauchy slice in space-time. And in particular, one can take the Cauchy slice to be Scri plus. And if one plugs in the solution, the general solution that I've shown before for an asymptotically flat space-time, one obtains a formula that looks like this. It looks a bit complicated, but we can break it down. So here on the first line, so first of all, I'm using a shear, this very simple shear that I showed before, that's just parameterized by CNN. So of course, these CNN functions enter. The bonding mass aspect enters as well. But the key thing is that this first line here is just a total variation in phase space. So this delta here denotes the exterior derivative on phase space. And hence, when one computes the symplectic form, which is given by the exterior derivative of this symplectic potential, the first line goes away, right? Because delta squared is equal to 0. And one is just left with the second line, which when one computes this exterior derivative, one obtains a formula like this. And this basically tells you that, confirms this claim that the zero mode of the shear and this memory mode are canonically paired. And the bracket is given by this function, which you can think about as just the Green's function for the Laplacian squared on a codimension 2 surface, in particular on the sphere. Now, another thing that you may wonder is, so from the symplectic potential, one usually, for example, in ADS-CFT, one thing to point out here is that unlike in ADS-CFT, right, where one usually imposes that the symplectic form vanishes near the boundary, here this is not the case, because we have both the first line and the second line. And it's known, however, since Gibbons and Hawking, that the variational principle can be made well-defined, provided that this object is a total variation of some quantity. And so in order to make the variational principle well-defined, regarding now Scri plus and Scri minus as a limiting boundary of the space-time obtained by pushing, say, a constant R surface, so a time-like surface all the way to infinity. The variational principle can be well-defined by adding a boundary action that is basically given just by this first line with this exterior derivative stripped off. However, we still have the second line here. So this tells us manifestly that the symplectic potential is not exact. So a priori, without imposing further boundary conditions, we cannot get a well-defined variational principle. But we do have two options, at least, from looking at this formula. So one of them is to impose that either delta C vanishes or that N vanishes. So in other words, either the zero mode of the shear is fixed or there is no memory. Now, we would like to keep the memory because we know that that's a fundamental feature of gravitational waves. So it's natural to just, for this simple example here, to fix the zero mode of the shear instead. So this is what we're going to do, and this gets rid of the second line, but I want to emphasize that once you do that, you also kill the symplectic form. OK, but for this problem, for the first question that I was asking, this is good enough, because one can now obtain an infrared on-shell action by just evaluating this action on a solution of Einstein's equations, and it's well known that the Einstein-Hilbert action vanishes on shell, and so we are just left with the boundary action, which takes this particular form. So a few comments are in order here. So first of all, you may be worried that this bonding mass aspect appears. However, as we saw before, this is related to this n and c variables via the GUU Einstein constraint. And so we can trade this for an order n squared term, as it turns out. However, its coefficient turns out to be infrared divergent. And one has to be careful about that. It's presumably related to the infrared divergences that appear in the Weinberg S matrix. However, it's not, the relation is not immediately obvious because those are obtained in a completely different way from scattering amplitudes in momentum space and so on. So for now, to just not have to worry about these issues, let's just focus on linearized fluctuations. So basically, just terms that are linear in n on top of a fixed c background. And this makes sense because we just imposed the boundary condition that delta c was equal to 0. So in this case, this object just collapses to the last term. Now, another thing that one may wonder about is whether this object is gauge invariant, and this would have to do, this would be very important in making more precise this connection between these memory geometries and the shockwave geometries that we saw before. And indeed, one finds that, so one has to go back to the expression of the symplectic potential, and indeed one finds that for diffeomorphisms or gauge transformations that depend on the field variables, as are those diffeomorphisms that relate the shockwave metrics to these memory metrics, this action is actually not diffeomorphism invariant. However, it can be fixed, as was shown a while ago by Donnelly and Friedel, by the addition of a corner term. And so once one adds the corner term to this action, as well as the contribution from scry minus, one obtains an infrared action linearized, again, linearized in n, with this particular coefficient. And this coefficient is going to be important in what follows. So there's two things that this action agrees with. So one of them is that it acts as the generating function for current correlators in a 2D CFT, as advertised before. And the other one is that this object is also exactly the same as the soft supertranslation charge, but where the supertranslation parameter is actually promoted to this Goldstone or this zero mode of the shear C. So as for the first point, let me be very brief on what's going on here. So we can associate, in principle, even including these quadratic terms in n, we can associate this on-shell action in the infrared with a partition function given by integrating over these soft gravitons, basically of e to the minus SIR. And due to this term that couples n and c, we see that one can show that this is exactly the generating function for 2D correlators of Katz-Moody supertranslation currents. So those turn out to be directly related to the soft gravitons and hence to n. And so in particular, differentiating with respect to c generates Fourier correlators of these n modes. And those were shown a long time ago to be dual, as I said, with two soft gravitons in the bulk. Now, another way that another interesting thing is that this on-shell action obtained here actually agrees exactly with a 2D effective action that was derived with effective field theory methods in previous work, basically by using the supertranslation symmetry and the shift symmetry of the Goldstone mode. And so that action, after integrating in this memory mode, precisely agrees at least to linear order in n with our on-shell action. So in some sense, this is a more closer to ADS-CFT derivation of these results. And finally, there may be some interesting relation that I won't have time to talk about between this action and partition function for edge modes in gravity. Okay, and since I don't have much time left, let me be very brief about the connection to the supertranslation charge. So the supertranslation charge is just given by the integral of the body mass aspect against the function on the sphere. And then using the constraint equation that I showed before, one can decompose this charge into two components. One of them is the hard part. So basically, in pure gravity, it would just involve a term quadratic in n. And there is this linear piece that is basically linear in n. And so on the support of this soft solutions that I introduced before, the soft charge just becomes this. And this is very familiar because it's just the linearized part of the IR action that we showed before. But crucially, in the standard derivation of these charges, this C is a function. Usually n is promoted to an operator. But since C and n actually don't commute, it's natural to conjecture that there may exist in quantum gravity an operator that would be relevant and associated to these charges where this function C is promoted to an operator. And if one does that, then basically this starts looking very similar to this kappa operator that we had before, where this C and n variables are analogs of this XU and XV variables that we had before, with the added fact that now we have an actual derivation of this commutator, non-trivial commutator between C and n. The upshot here is that fluctuations in this new bilinear operator in C and n are proportional to the area just as before. So this is interesting. But we still don't understand it very well. You may be confused because naturally this soft charge exists also in the vacuum, so you don't need to have matter, whereas the modular Hamiltonian, especially in the case of the shock wave, is associated with the matter stress tensor. And one way to make sense of that is to consider the shock wave scenario with body mass equal to 0, in which case the net large gauge charge vanishes, which means that the soft and the hard charge are equal to one another. Then from the constraint, you essentially deduce a relationship between this boost, or really like supertranslation generator, and the soft charge. So to summarize, what we have shown is that there exists an on-shell action in the leading sector of gravity in four-dimensional asymptotically flat spacetime, so this is non-trivial. We have shown that by fixing in this action the zero mode, well, to obtain this action, we actually had to fix the zero mode of the shear or the Goldstone, and in this way, we recover a dictionary that relates the on-shell action, or really the partition function associated to it, with the identifies that with the generating function of 2D correlators of Katz-Moody currents dual to 4D soft gravitons, correlators of soft gravitons. And then we also showed that there seems to be a relationship between these boundary actions and the soft component of the supertranslation charge, and that allowing for the supertranslation parameter to fluctuate leads to a new soft charge operators which is naturally, by the way, defined on the celestial sphere, and whose fluctuations seem to capture some information about area fluctuations of causal diamonds in spacetime. So there is many open questions, so let me just outline three. So one of them is, why should this C be promoted to an operator? And another one is that I've done this analysis at infinity. Can we generalize it to finite distance? Another one is the connection between what I said and edge modes in gravity. And finally, one can ask, basically, if we can measure these operators, QS, in an actual experiment. So with that, thank you very much.
Thanks a lot. Questions for Anna Maria? Yes. Dan.
Hi, Anna Maria. So if you add matter fields, then the bulk Lagrangian doesn't vanish on shell anymore. Do you have any comments about that?
Yeah, so that is a good question. We didn't consider the addition of matter fields yet, but we know from studies in Maxwell theory that that is a little bit more subtle. So it's a good question. I don't know. I haven't computed it.
Thank you for the talk. I was wondering, this effective description that you have in terms of n, How am I supposed to understand n? Is it, are you integrating over n of u n z comma z bar, or just n of z comma z bar?
Yeah, so sorry if it wasn't clear.
Yeah.
So maybe let's go back. So this n here is just a function on the sphere, but it is the coefficient of a this time-dependent step function that appears in the news. And actually, so this n is really, one can prove that it's just literally, well, up to some coefficients, it's a it's the leading soft term in a momentum space, like expansion of this object. So if you take the news and you take a Fourier transform and then you take the omega goes to 0 limit, this is literally like a soft mode. And the soft modes from works by like a long time ago are via the soft theorems, one can show that those are associated with these Kac-Moody currents in a 2D CFT. And so the n is related to those currents as well.
Okay. So the question that I had next was, if I take seriously the path integral over n, can you relate this? I mean, presumably this is a very simple theory. This is computable. You should be able to relate this to a piece of the ordinary path integral of Einstein gravity of one loop.
Absolutely. I agree with that.
Is this something that you have done?
It hasn't. I don't think it has been done, but I think it should be. I mean, these modes should exist. So one can, for example, start maybe with a 2D model of flat space gravity, and I think in that case, there's still some sort of supertranslations, and there should be some analog between these n modes and the path integral over them and the Schwarzian modes that appear in ADS. So, yeah.
Thank you.
For a last question. What has a question?
You motivate, one of the motivations was to understand better this work by Surek and others, where there were some effects that seem to contradict the ordinary perturbation theory.
Yeah.
Did you understand what the conclusion is?
First of all, the thing that I think was confusing here, so usually we compute this two-point function of linearized graviton fluctuations, and that's, it scales as Planck length squared, as one would expect. The funny feature about these operators that they introduced and they used to compute to get this enhanced scale is that they're actually quadratic in this guise, and that these two, basically the supertranslation boost, if you want in this case, when you look at the subregion, you have the boost parameter, xu, and then you have this shift, the time delay of the probe. And both of them were regarded to be operators and have these non-trivial commutation relations. And these were highly non-proved. They were just postulated by 't Hooft, and yeah. But in asymptotically flat spacetimes, it seems reasonable that one will be able, so let's go back now to the supertranslation charges. So the soft component of the supertranslation charge is something that looks like this. Usually here we just have a function on the sphere, but now I'm proposing for a moment to take that function on the sphere to just be the Goldstone. And that makes sense because we have, if you think in the quantum theory, you don't have just one vacuum, you have an infinity of vacua, and you can think about the C operator as measuring which vacuum you are in. And so it's natural to conjecture that one may be able to construct an operator that's bilinear in the Goldstone mode and this memory mode, whose expectation values in one of the BMS vacua is just the usual normal supertranslation charge that one would usually construct, where the C then becomes, takes the value of whatever vacuum you are in. But this is a more general operator, and then one can ask questions about like what does it mean? What are its fluctuations? Of course, you can compute its fluctuations in various states, but if you do it in the vacuum using the commutation relations between, and another thing that it's natural to do that because we know that this Goldstone and memory modes actually are dynamical. They exist on the boundary of asymptotically flat spacetimes, and their commutators are non-vanishing. And so, yeah, so this is a fact. It's proven, and so one can hope and one can, to rigorously compute basically correlators, at least of these operators in all sorts of states. in asymptotically flat spacetimes. I mean, that has not been done, but a preliminary sort of calculation, very sketchy one, indicates that fluctuations in this operator in the vacuum do scale like the area of the celestial sphere, if you want. So in that sense, if you take that for granted, and well, this is a fact, and then if you then are able to show that somehow these operators do indeed capture area, like properties of the area, then indeed here you would be able to reproduce the relation of Ferninde and Zurek, perhaps in a bit of more rigorously. Hopefully, that would be the hope.
I'm really sorry, and I can ask you later, but is the claim that you can do an experiment in a laboratory where the fluctuations are enhanced, or what do you expect?
I am not the person to ask that question, but Catherine actually does have, well, Catherine is doing an experiment that will probe something. I don't fully understand that, but yeah.
Okay. Good. So, on that note, thanks a lot, Anna Maria, for the inspiring talk. So the last speaker of the morning session is Natalie Paquette, and she will talk about Carroll algebras. Take it away.
Thanks. Can everybody hear me? It sounds on. Okay, great. Well, thanks very much for the introduction. And of course, I'd like to start by thanking the organizers for the invitation to speak here today. It's a pleasure. And also, if I may, I'd like to take a moment to thank the staff of this conference as well. Everything has just been running so smoothly, and they've been doing such a spectacular job. So thanks to everyone involved in the conference. So today, I'm going to be talking about a special and relatively tractable class of four-dimensional massless quantum field theories that I call twistorial quantum field theories, for reasons that many of you probably already know or will hopefully become clear. And the tractability of these theories can be expressed because of, or one way to express the tractability of these theories is because they have very, very close connections to two-dimensional chiral algebras. So I'll explain some of the new progress that we've made in better understanding these chiral algebras and how they can control scattering problems in this special class of massless 4D field theories. So to the extent that I say anything new today, it's based on work done in collaboration with these two gentlemen. Mostly, I'll focus on the paper that came out just last month with my former graduate student, Victor Fernandez. And time permitting at the end, although I promise not to stand between everyone and lunch. If I don't get to it, please ask me after. I'll also try to make some remarks about a paper that appeared in collaboration with my former postdoc, Nick Garner, who's now a postdoc at Oxford. And both of these works build crucially off of previous work that I've been developing over the past few years, largely in collaboration with Kevin Costello. I'll try to state some of the fundamental background results. In view of time, I'll have to be a little bit brief. But if you're interested in more of the details of some of the results that I'll just kind of state as given, there are a few talks already online about more of the background of this work and kind of why these things fit together. Okay. So the plan of the talk is as follows. First, I'll introduce what I mean by twistorial quantum field theories, what class of objects am I studying. I'll then try to motivate a little bit why I'd like to study such special theories. Admittedly, they are very special. Of course, I don't have to motivate to theoretical physicists why we look for various toy models, but I hope that these theories are also perhaps useful more broadly. Then I'll introduce the two-dimensional chiral algebras that, as I've mentioned, turn out to govern scattering in these special twistorial quantum field theories. And then I'll mention, finally, the new result, in particular the work with Victor, where we now have really good and, in fact, complete analytic results for the chiral algebras in question. So just very briefly speaking, to kind of flag post the result, these chiral algebras have operator product expansions that control the collinear singularities of scattering in these twistorial quantum field theories. The OPEs, in principle, because these chiral algebras have a deformation parameter called h bar, the coefficients can get corrected order by order. As in principle, there's an infinite number of these coefficients. And the parameter is called h bar because in 4 dimensions, it coincides with the usual loop counting parameter. So you have these singularities, in principle, to arbitrary loop order. And, well, Costello and I proposed that you should use these chiral algebras to expediently calculate form factors in these twistorial quantum field theories. And if you wish to push this program to higher and higher loops and get as much out of it as you possibly can, you need to understand the chiral algebra OPEs in principle to these higher and higher loop orders or deformation orders. So finally, after a lot of blood, sweat, tears, and one PhD student's term of employment, we finally finished that result this December, and the paper's just appeared. So that's the punchline of the talk, if you care to zone out afterwards. And time permitting, I'll mention that some of these chiral algebraic constructions can also be generalized to some special twistorial backgrounds, not just flat spacetime, and then conclude. All right. So first, what are these theories that I'm studying? Twistorial quantum field theories. So as I said, today our interest is going to be in a special class of four-dimensional massless quantum field theories. They are not necessarily supersymmetric, and indeed I'll focus primarily on the non-supersymmetric examples of these theories. But nonetheless, they're incredibly simple because they do enjoy a tremendous amount of symmetry, just not supersymmetry. They are in fact integrable. And one way to understand that integrability is in terms of this geometrization using twistor space. So I'll say a few more words about that, but that's why I call these theories twistorial quantum field theories. Their close connections to twistor space turns out to render them integrable. Now, because of this, they only have trivial S matrices in flat spacetime, but it turns out that these theories nonetheless have non-vanishing form factors, meaning scattering amplitudes in the presence of additional local operator insertions. So these are non-zero observables that you can compute. And in this talk, I'll focus on the case of a form factor only with a single local operator insertion. The generalization to multiple local operators, I think, is very interesting, but less understood by us currently. So in brief, these theories are essentially self-dual gauge theories coupled to matter, particularly the examples I'll be focusing on in my talk today. And it's been known for many, many years and codified in even a textbook at this point that the classical integrability of self-dual gauge theory, one avatar of this property, is the existence of a six-dimensional description in terms of a local holomorphic field theory living on twistor space. So I won't have time to review sort of how all of this works, but again, it's classic and classical stuff. So what is twistor space? For the purposes of this talk, well, of course, as I said, it's a 6 real dimensional manifold, but it has a complex structure, so it's a 3 complex dimensional manifold. And in particular, I'll always be working in a complexified setting, so I'll be thinking about complexified 4-dimensional space-time C4. And very heuristically speaking, the twistor space associated to complexified space-time C4 is a manifold such that for every point in C4, there's an associated CP1, or topological 2-sphere. And these spheres in twistor space can intersect with one another if and only if the corresponding space-time points in C4 are null separated on the complexified light cone. And much of the simplification of the scattering of these theories and their very restricted analytical properties is kind of downstream of this geometry of twistor space in words. Well, so in particular, if I focus on the real slice associated to Euclidean signature, then from what I've just said, of course, all the associated spheres should be disjoint with one another because they only intersect when they're null separated. And as a real manifold, you can think of twistor space as R4 cross CP1. So if you're not very familiar with it, it's not too important for this talk, but that's sort of the picture you can have in mind of what this space is. Now, so classically, as I said, self-dual gauge theory and its twistor space connection has been understood for a long time. So in 4 dimensions, I'll write schematically a BF type action, a Chalmers-Siegel type action. And it lifts up on twistor space to another action of BF type, but now in terms of holomorphic fields. So I denote all holomorphic fields by curly letters instead. And Mason showed very carefully that indeed, if you do a dimensional reduction of this theory upstairs along CP1, you do indeed recover the theory downstairs. And if you're a classical physicist, well, all is right with the world, and this works very beautifully. But today, I don't want to think about self-dual Yang-Mills theory by itself. because there's actually a famous obstruction to the integrability of that theory in 4 dimensions at the quantum level once you consider loops. Indeed, self-dual Yang-Mills has a non-vanishing 1-loop amplitude with all positive unicity states. And in particular, all of the theorems that Costello and I proved and all of the mileage that we get from these kinds of constructions rely crucially on the existence of this twistor space uplift. So if I want to apply these theorems, I in particular need the twistor space uplift to continue to exist at the quantum level. But in general, a holomorphic theory can suffer from a gauge anomaly, which you can think of as an obstruction or failure of the integrability of the 4D theory that lives downstairs. But nonetheless, I want these twistorial theories to exist because I want to leverage all of their extremely nice and simplifying properties. So I have to cancel the gauge anomaly and make sure that the quantum theory in 6 dimensions is still well defined. And in recent years in particular, Costello has really studied this in a lot of detail. And there are now quite a few known ways to cancel the anomaly. So when I say twistorial theories for the remainder of this talk, I mean theories that are twistorial still at the quantum level, for which I've canceled the gauge anomaly, which means I have to deform the self-dual gauge theory in some way, in particular by coupling to some special matter that does this job for me. So without going through the details, let me just kind of briefly say a few ways you could cancel the anomaly, and then I'll get to some examples of self-dual gauge theories that do this. So, of course, supersymmetrization works, and since the beautiful seminal work of Witten on 4D n = 4 self-dual Yang-Mills, we know that the twistorial theory there is good and extremely useful. But I'll focus on non-supersymmetric theories today, and therefore other means of canceling the anomaly. My strings talk in 2022, which some of you might have heard, emphasized in particular a Green-Schwarz type mechanism for certain Lie algebras, gauge algebras G, that does serve to cancel the anomaly. I won't dwell on that too much today, but you couple in some extra matter that in 4 dimensions gives you kind of a funny pseudo-scalar field in 4 dimensions that we called the axion because it couples to a trace f squared term down in 4 dimensions. So that's one option for certain G. It's certainly interesting, but there are also particular choices of G and real matter representations R that can do the job without this extra field. And more generally, again, depending on the details of the gauge algebra and the representations, there can be combinations of these 2 mechanisms with the Green-Schwarz field and some additional fermionic matter, and together they render the theory consistent. Others in the audience might be familiar with other interesting examples of holomorphic anomaly-free theories that have close connections to the topological string and have been useful recently for explorations in twisted holography. I won't talk about any of that today, but some of you may have seen my collaborator Atul Sharma's talk on this at a previous strings conference, and he's also here in the audience as well. Okay, so here are some of the twistorial quantum field theories that I'm interested in today, and anything I say about chiral algebras applies equally well to any of these examples, so I've just made a list of a few such options. Perhaps maybe the simplest one, or the one to keep in mind, is having gauge group SU3, self-dual gauge theory, coupled to 9 fundamental flavors of Dirac fermions. So, of course, not the amount of matter we would be interested in for massless QCD in the real world. We know that massless QCD is, well, quite complicated. But nonetheless, at least there's some relatively familiar matter here to play with. And there are similarly also nice combinations, as I said, including this Green-Schwarz field and fermionic matter, such as N flavors with SUN gauge theory. And you can go on and play this game and find many such examples. OK. Now, why do I want to study these things, other than my obvious predilection for chiral algebras? Well, general motivation might be the following. Of course, we know if we're interested in studying scattering amplitudes in general 4D non-supersymmetric quantum field theories, like QCD in the real world, typically we have to work very hard to compute amplitudes at progressively higher loop order or with progressively more external particles. And there are, of course, many ingenious ways to make progress on this front, and a lot of heroic work, including by many experts in the audience here. But I think it's fair to say that it always behooves us to keep searching for new theoretical or mathematical structures that might assist us in some corner of this program and to add to our existing toolbox and hopefully get some new mileage. Now, the twistorial theories that I'm studying today, because their scattering, as I've mentioned, is completely controlled by a 2D chiral algebra really only have rational form factors. I mentioned these theories were massless. So in the complexified setting in which I'm working, well, or in general for a massless theory, p squared is always equal to 0. So we can split the momenta as usual into spinor helicity variables of positive and negative chirality. And because I'm complexifying everything, I can kind of take a limit where the angle brackets of two of the positive chirality spinors go to 0 without touching the square bracket inner products. So this is sometimes called the holomorphic collinear limit. It's a very useful thing to do. And these twistorial quantum field theories have form factors only with poles in the angle brackets. So incredibly simple analytic structure, none of the interesting branch cuts or transcendentality of quantum field theories like QCD that are more general. And this follows precisely because the form factors in these theories can be computed using a chiral algebra. And Kevin and I have called this the chiral algebra bootstrap program, leveraging the existence of an inherent 2D chiral algebraic structure to compute form factors in these twistorial theories at higher and higher loops. So the singularities are entirely fixed by the chiral algebra OPE that's associated with this kind of holomorphic collinear limit. So if you want to compute some form factor at some given loop order, you know exactly where its poles are if you know the chiral algebra OPE. And then in turn, the residues of those poles are themselves form factors, either at lower loop order or with fewer insertion points. So you can recursively simplify your problem, which is computationally, of course, very expedient compared to the usual hard work that you have to do for more general theories. And that again, is what we call this chiral algebra bootstrap program, this method for computing these things. And in particular, I want to stress, in QCD, for example, to go from, say, a 4-point amplitude to a 5-point amplitude, just the addition of one additional external state, is a great deal of work. It's very non-trivial. So in these theories, I also want to emphasize that the chiral algebra bootstrap makes it essentially trivial, very easy to use induction on endpoints and get general endpoint results. So that's a nice feature. OK, so twistorial QFTs are clearly a nice toy model. But also, they're self-dual gauge theories coupled to some special choice of matter. Unfortunately, I can't rid myself of this finely tuned amount of matter that I have to couple in by construction. That's sort of the price of the simplicity of these methods. But nonetheless, remembering that in gauge theory, this self-dual gauge theory computes some observables in ordinary gauge theory, in particular those with the simplest possible external helicity configurations, means that at least I'm learning something about some small subsector of Yang-Mills theory coupled to this twistorial matter content. And amplitudes of even special helicity configurations can still be useful input in various recursive methods and so on. And let me also briefly just mention that there's a nice recent paper by Lance Dixon and Anthony Morales, who used these twistorial anomaly cancellation conditions that I was just telling you about, and they actually found some new relationships among one-loop and gluon QCD color stripped amplitudes, so the kinematic dependence of some one-loop amplitudes. So it does indeed seem that really paying attention to some of these twistorial constructions might perhaps be more useful to give us other more general lessons. Certainly that's my hope, and I think this is a nice preliminary example. So this slide just gives a bit more flesh to what I said in words on the previous slide. Self-dual gauge theory with special external helicity configurations compute the corresponding diagram in gauge theory for you. So here again is just my self-dual gauge theory written in Chalmers-Siegel form, where B is an anti-self-dual two-form field, which you should think of as encoding the negative helicity gluons. And the gauge field A encodes the positive helicity degrees of freedom in this formulation. And so self-dual gauge theory has a plus-plus-minus propagator, or a plus-plus-minus vertex, but not its parity conjugate in particular. So there's not too many interesting diagrams you can draw with self-dual gauge theory on its own. Of course, I'm always having in mind the case with twistorial matter. I'm just suppressing that on this slide. But it's also known that if you take the Chalmers-Siegel action and deform it with a trace B squared type term, you get a theory that's perturbatively equivalent to ordinary Yang-Mills. So if you're in the business of computing form factors, the natural local operator to start with would be a trace B squared operator that essentially should compute some simple amplitudes in Yang mills for you and would correspond to the addition of this extra bivalent vertex. So this is the first natural form factor to compute using chiral algebra bootstrap techniques, the addition of a single insertion of trace b squared. And indeed, you can draw these, you can play with these Feynman rules and convince yourself that what you'll get are particular 2-loop, 1-loop, and tree-level diagrams, again with special external helicities, respectively 2 minus, 1 minus, and all plus such amplitudes. And we computed these with the chiral algebra bootstrap in previous work. So at least that part is done. And in particular, another recent paper by Dixon and Morales provided a sanity check on the 2-loop result with this twistorial matter, which is novel. Of course, the traditional methods, they so far have been able to check 4 points only, and the chiral algebra result, as I stress, is an endpoint result, but nonetheless, you find nice agreement there, so the proposal at least seems to be working. More generally, there are other interesting local operators that one might wish to put in a form factor and match to the associated gauge theory observables, again, essentially with all plus external helicity configurations. But as I've been saying, to push this to higher and higher loops and compute some other interesting form factors, you need control of the chiral algebra in order to run this program. In particular, you need to know it to arbitrary precision, or the desired precision, in what translates to the loop counting parameter in 4 dimensions. So I've been advertising this chiral algebra. It underlies all the nice things I want to tell you. So what are these chiral algebras and where do they come from? So I'll be brief. Again, there are many more details about the background in my Strings 2022 talk, or Ask Me After. But in general, the theorem is that given a local holomorphic theory on twistor space, in particular one that's well defined at the quantum level, so gauge anomaly free, well, I've already told you that you can associate to that a 4D twistorial quantum field theory by dimensional reduction on P1. And the miracle there is that you don't get any Kaluza-Klein mode, so a local theory in 4D can also be described as a local holomorphic theory in 6D. And you can also construct a 2D chiral algebra, whence this theorem begins to be useful. Oh, okay. For this talk, in view of my increasingly short time, the elements of the dictionary to keep in mind are just the following. The operators in the chiral algebra correspond to my scattering states in 4 dimensions, massless matter fields of positive and negative helicity, and the positive and negative helicity gluons. And the OPEs, as I've already said, are these holomorphic collinear limits in 4D in the complexified momentum. And these chiral algebras at the classical level, as you may have heard, we've heard a little bit about the W infinity. Classically, they've been studied in terms of their relation to asymptotic symmetries and so on, but I won't talk about that aspect of them. Okay, so what is this chiral algebra and where does it come from? Well, in order to get this chiral algebra, at least in principle, the theorem guarantees the existence of this chiral algebra. That's what I want to emphasize. In practice, how do we actually get access to the OPEs to the desired order that we want? The 6D construction that in principle tells you how to obtain the chiral algebra is as follows. You consider coupling the holomorphic 6D theory to a general holomorphic 2D theory supported along one of the P1s in twistor space, say the P1 above the origin in R4, for example. And by construction, we assume that the 6D and 2D theories are themselves gauge anomaly free, or BRST invariant. And we write down the most general possible coupling between the 6D theory and a putative 2D theory. And we ask what constraints the gauge anomaly free condition, or BRST invariance, of the corresponding coupling gives order by order. So in principle, this is a calculation you can do. It looks kind of like a holomorphic generalization or analog of a generalized Wilson line. So there's, say, a curly AJ type coupling, where J is again a current in my arbitrary 2D theory. It's constructed in some way from local fields and derivatives of that theory that I don't need to know the details of. And I simply require, expanding this exponential in my path integral, that all BRST variations cancel amongst themselves. And that, in turn, gives me constraints on the singular term of the OPE. Rather analogous to how, in ordinary gauge theory, we can derive the current algebra of the gauge algebra in terms of commutator of currents. So there's such a coupling for curly A and J. Those encode the positive helicity degrees of freedom, as I mentioned. There's an analog for curly B and, say, other currents J tilde that give you the negative helicity stuff, and additional couplings as you add additional matter that I'm suppressing here. So this is in principle what you would do, but in practice that means order by order in perturbation theory. You have to write down some Feynman diagrams at higher and higher loop order in this holomorphic coupling, compute their BRST variations, and demand that they all cancel. So quickly, that gets to be laborious. So can you do a little bit better? And the central result of this talk is that you actually don't need to work that hard, although you can make your PhD student check your work by computing some at least one loop diagrams before you decide you're torturing them too much. I stress that if the 6D theory has that gauge anomaly, like if I were just doing holomorphic BF theory by itself, the chiral algebra would fail to associate. But given a non-anomalous 6D theory, the theorem guarantees that there is a well-defined associative chiral algebra. It certainly exists. And so what Costello and I also did a couple of years ago, just at the one loop level, was we say, well, let's just use associativity. It's guaranteed to exist. Let's require that this chiral algebra is associative at the one loop level and derive the OPEs from that kind of bottom-up consideration. So you can do that. You get a crucial extra term that is absent in BF theory by itself, with a coefficient that's fixed by the anomaly cancellation condition on twistor space, and you correct to a nice associative chiral algebra. So at one loop, we were able to just use this kind of simple kind of workman's-like approach to get the one loop chiral algebra. It was checked using holomorphic integrals, and we were happy. And the central conjecture is that, well, if you believe my theorems, then by formal nonsense, this chiral algebra exists. Perhaps optimistically, you can use the knowledge of all the symmetries that the twistor theory enjoys. We know, of course, what the couplings look like. Perhaps we know something about which Feynman diagrams are BRST invariant. And let's put all our basic knowledge together and plus requiring associativity and try to just fix the chiral algebra that way without having to work, well, you work hard, but maybe less hard than you would otherwise have to. So perhaps that's an optimistic conjecture. Of course, those of you that know me know that I'm obviously an optimist. So we rolled up our sleeves, we got to work, and the central result of this talk is that, yes, it turns out you're able to completely fix the chiral algebra, or equivalently the collinear splitting functions of the 4D theory, to arbitrary loop order. So we have analytical results for that. And in view of time, which I think I'm already, yep, we'll wrap up. So let me just briefly say what the method is one more time, and then I'll conclude. So to fix the OPE corrections, first we just determine the general form of the OPE corrections using all of the stuff that I said in words a moment ago. There's a lot of symmetries in the game, scaling symmetries, 2 copies of SL2C from the complexified Lorentz group, and so on. Putting this together, you actually get the general form of the OPE corrections, and it turns out that you only have poles in 1 over z squared and 1 over z. That's all that's allowed, even though the coefficients, again, are interesting numbers order by order. And then we write down equations from associativity in the chiral algebra sense, which you've probably seen in your 2D CFT textbook. We massage them a little bit, get the minimal set of equations. There should be like a step 2.5 question mark, question mark, question mark, blood, sweat, tears, et cetera. But then you can, with some work, solve these things and get the coefficients. Okay. So in view of time, I'll of course skip the details. If you're interested, feel free to ask me after. There's also beautiful connections with homotopy algebras that provided some checks on our methods, which work beautifully, but I certainly won't talk about homotopy algebras in view of time and in view of audience patience. So let me just conclude. So the summary is that twistorial quantum field theories are a class of integral but not necessarily supersymmetric 4D theories that are characterized by the existence of this local uplift to twistor space. The basic observables are form factors, and form factors with a single local operator insertion are controlled and computable in terms of a 2D chiral algebra using what we call this chiral algebra bootstrap. And we have just shown that now the chiral algebra OPEs can actually be fixed by some elementary symmetries and associativity. So that effectively solves these theories for us, or at least now in principle, we can write down form factors at higher and higher loops, run this program, and we have the input that we need to now finally do that. And what I didn't have time to tell you about today, but if you are interested, catch me during a coffee break. We also generalize this method to scattering in the presence of some particularly nice self-dual backgrounds with a self-dual dion in gauge theory is kind of a nice application there. So in the future, there's many interesting things to do, of course. For me, my pressing interest is form factors now with multiple local operator insertions. How do you deal with them? There's a lot more to understand there. They're much more complicated for reasons that I can tell you about offline, but they give you access to more diagrams with more interesting helicity configurations, so I think it's very worth pushing on that and seeing if we can make progress. And finally, the more general and perhaps the grander hope is that these twistorial theories, of course, are coupled to finely tuned quantities of matter. Can we take the chiral algebra bootstrap as one small tool in our toolkit, use other things that we know, maybe computation of some fermion loops, and learn something about theories with more physically relevant amounts of matter? Perhaps maybe the chiral algebra could help us with maybe some rational terms or kinematic aspects of the rational terms and so on. Can we use this, adding it to our toolkit? So that, of course, is my biggest hope. But I'll thank you for your attention and your patience. Sorry for running over time.
Thanks a lot. Questions from the audience? Grumiller.
Thanks for a nice talk. In string theory, the n equal to 2 strings give you self-dual gravity and self-dual Yang-Mills.
Yes.
And they relate to n equal to 4 topological strings. What is the relation to what you were discussing to that?
Yeah, I would say that the n equals 2 and n equals 4 theories, if you view them in terms of the closed and open string field theories of the topological string, those are holomorphic spacetime theories. They're anomaly free on twistor space, and but they give you interesting examples of twistorial theories. But actually, sorry, let me clarify. Do you get self-dual gravity, say, by itself, or with some extra stuff maybe that could cancel this anomaly?
No, self-dual gravity by itself.
Okay.
And you get vanishing theorems. This is some things that we did with Hiroshi and also with Nathan.
Mm-hmm. Yeah, so self-dual gravity by itself, again, has a chiral algebra that we know fails to associate at one loop. Doesn't mean the 4D theory isn't interesting. It just means that the integrability properties that I've mentioned here can't be directly applied. In other words, the holomorphic collinear limits would cease to be universal in the 4D theory. But I think, these are clearly very interesting theories, and perhaps...
Well, the string theory makes sense. That for sure is an anomaly there, because you can compute them, for example, all loop amplitudes for certain backgrounds, so they make perfect sense.
So maybe there is a direct relation there. Indeed, we can talk more offline, but then the coupled open and closed string theory could be twistorial, and then you could run this program.
Other questions? Oh. Sorry. I didn't see.
Do twistorial QFTs have a non-perturbative definition?
Oh, that's a great question. I've really been focusing on the perturbative sector, of course. Yeah, I've thought about this only briefly, and not enough to say anything with confidence. I think the non-perturbative sector would be interesting to think about more. Well, of course, people have thought about the 4D n equals 4 self-dual Yang-Mills case, which is twistorial, and there's much that could be said there.
Matthias?
Can you say something about what sort of chiral algebras you get? You said you only have double poles, so there is no stress tensor, there is no Virasoro algebra?
That's right. They all have central charge 0.
Algebras, or what sort of, do you get current algebras?
Yeah, that's right. So classically, you get things like the W1 plus infinity algebra that was alluded to in the gravity case. In gauge theory, you get a generalization of a Katz-Moody algebra. Most of the generators have negative conformal dimension, so they're non-unitary. They have vanishing central charge, as you said. These are just big kind of floppy symmetry algebras, if you like.
Any further questions? Okay, let's thank Natalie again for the inspiring talk. And it's lunch.